All right, well, let's get started. Welcome to the September Bridge Builders Seminar. This is actually our 5th seminar, and we will finish the year with 7. And it's made quite a bit of progress, and it's thanks to you guys who show up and listen to what God is trying to reveal to us and talk and tell us. And I want to just recognize the speakers that have been in the past and the present and will be doing in the future, because these gentlemen put in a tremendous amount of effort into these presentations. So I just want to have a moment of appreciation for them. All right, well, we're so glad you're here. As I said, this seminar would have no meaning if people weren't here to listen. And so, just a few requests or comments before we get started. During the presentation, we're going to keep these doors closed because they affect the cameras because of the hallway lighting. So if you need to leave the room, please exit this door on the right or your left. All right. So, and secondly, if you are sitting up in the gallery, if you would exit through the center aisle, because we've got some caution signs which are more for me than you, but it would help if you'd go out that way, feet into the center and out that door. That just makes it better for us and less commotion for the cameras. And please be aware of the cameras around. I've tried to place them completely out of the way as best I can, because recording these presentations really helps us not only to have an archive, but more importantly to reach those people who are not able to make it. Or, in your case, maybe you want to watch it again and to have even more knowledge of what was said. So we'll be moving quickly today because we have a lot to cover. I doubt we'll make the time frame, but that's okay. God's timing is not our timing. So let's get started. I'd like to start with a scripture reading, Proverbs 3:13 through 20. Blessed is the one who finds wisdom, and the one who gets understanding, for the gain from her is better than gain from silver, and her profit better than gold. She is more precious than jewels, and nothing you desire can compare with her. Long life is in her right hand. In her left hand are riches and honor. Her ways are ways of pleasantness. All her paths are peace. She is a tree of life to those who lay hold of her. Those who hold her fast are called blessed. The Lord by wisdom founded the earth. By understanding he established the heavens. By his knowledge the deeps broke open, and the clouds dropped down the dew. Let's pray. Our Heavenly Father, we praise you for you providing us this universe, this planet, and this conspicuous design which pervades them. Just as we praise and thank you for the sacrifice of your Son Jesus on our behalf, through whom you forgive our sins. We praise you for your word and your spirit which inhabit us as believers, and pray these seminars increase our faith and awe in you. In Jesus' name. Amen. So our first speaker today will be Glenn Salisbury. This is his second time to present, so we're very thankful for that. Glenn has been a member of our church for about 7 years. He has a BA in physics from UC Berkeley in 1975 and an MS in physics from Cal State University at San Diego in 1981. His career spanned over 39 years with extensive experience in stealth technology working at Lockheed. Because of this background in stealth technology, he may be difficult to see today because he's stealth. It might, on your phone or whatever, he may appear about the size of a walnut. So that's the way stealth works. It is my pleasure to introduce Glenn Salisbury speaking on the sun and its effects on the earth. Glenn?
There we go.
Let me get your mic on.
Okay.
Okay, I got
Are we wired for sound now? No. Now we're wired for sound. Okay. Oh, thank you. Thank you for being there. Listening to the talk I'm going to present. And this talk is on the sun and how it affects the earth. So I thought I'd begin with the creation of the sun, Genesis 1:14 to 16. And God said, "Let there be lights in the expanse of the heavens, and to separate the day from the night, and let them be for signs and seasons, and for days and years, and let them be lights in the expanse of the heavens, to give light upon the earth." And it was so. And God made the two great lights, the greater to rule the day, and the lesser to rule the night, and the stars. And so the sun was created. In this talk, I'm going to be talking about we'll start out with the standard solar model, the light that comes out from the sun, the magnetic field of the sun, solar wind, solar flares, and then there's an alternative model to the sun that is gaining popularity that I wanted to cover also, because it will affect how people look at things. This is part one of two. The second part is more about how the sun affects us physically in human biology. This one is going to be more about how it affects technology, the physical aspects, and what all these effects are that lead to all of this. Okay, the standard model of the sun. This is what they talk about. The sun has a diameter of about 1.4 million kilometers, and its mass is 2 times 10 to the 30 kilograms, and it puts out 3.86 times 10 to the 26 watts of power in all directions. Now those are unbelievable numbers. It's like 800,000 miles across, and you can't even begin to describe how heavy it is and how much power it puts out. But it has a core, then followed by the radiative zone, where the size of the star is determined by the light pressure, then a convective zone, which is heat transfer by convection, and finally you get into the top levels, the chromosphere and photosphere and all of that, characterized by sunspots, granules, and we'll get into that. Sunlight. First thing we know about the sun is it makes lots of light. At the Earth's distance, the average is 1,361 watts per square meter outside the Earth's atmosphere. It sounds like a lot, but really if you're trying to do anything with it, it gets to be a lot of work to make it concentrated enough to get materials processing or anything other than just growing plants. You're in trouble. It's hard. You can see from the map that there are places where the sun gets, places get more sunlight than others. Sometimes not what you'd expect, like equatorial Africa. You don't expect, that's right on the equator, you'd expect it to get a lot of light, but there it is showing up with a cooler color. Of course, that's cloud cover and things like that being taken into account. When you get light from the sun, you get it according to a spectrum. The yellow curve on the top here is outside the Earth, and the orange is what hits the Earth's surface. This is characterized by what are called Fraunhofer lines, which are these dips in the solar intensity caused by ozone and water vapor and carbon dioxide and all these other things that are in the atmosphere. The visible light that you actually see is marked in pink. The rest of it you don't see, but it's still there. You get warm from the sun because of infrared, for example. It has some simple effects. It's heating. The amount of power is very well balanced for what we need as a planet. We're not too hot and not too cold. The Goldilocks zone, they call it in the literature, because of that. If it gets out of that, you get out of that, things happen. You can't, you don't stay alive if it's too hot or too cold. As side effects, we get sunburn from the sun, and it bleaches things like clothing and paint and so on. And organic chemicals break down in sunlight because of the ultraviolet, and rubbers and plastics and so on. The sun is characterized by certain physical features. Sunspots, prominences, filaments are the most common. The granules, you can barely see them here. They're really kind of small and they don't have individually much effect on us. Collectively they do, but individually they don't. You get into things like solar faculi, which is white spots on the surface, and filaments, which are plasma tubes that lie near the surface and sometimes lift off. And then you get prominences, which are explosions off the surface of the sun. The sun is characterized by a series of cycles. If you count the number of sunspots and plot them over the years, you get charts like this. And it varies. And if you go back further than I've gone here to the 17th century, you get what's known as the Maunder minimum. And the Maunder minimum, there weren't any sunspots for several hundred years. And they had weather problems and changes because there were no sunspots. When the sun is active, the sunspots are there, the power output of the sun is a little higher, radiation output is higher, so you get all this stuff aggregating effects that actually increases the temperature on the Earth by 0.2 of a degree Celsius, depending on what part of this cycle you're on. The sun has a magnetic field, and I once heard it described as looking like a skein of yarn after the cat got hold of it, because it goes everywhere and does everything. In the open areas, it's about 300 to 500 Gauss. Now the average field of the Earth is a little less than half a Gauss, so you get this figure that it's 100 or it's 1,000 times the strength of the Earth's magnetic field. That applies in the open areas. In a sunspot, it can get to 4,000 Gauss. And that's like the very strongest refrigerator magnet you ever saw, is about that much. And these magnetic fields, of course, they don't stop at the solar surface, they extend out. You can measure the magnetic field at Earth, and there are people that categorize that, and how it's tilted determines certain aspects of space weather. It's not always, straight out or straight up and down or anything like that. It moves around with the Earth, with the solar wind pushes it, solar flares push it, all kinds of things. It's very variable. Okay, solar wind. This is actually from I think Wednesday. It looked like this. And what this is where the solar wind is coming out. And when that gas comes out and expands, it cools and it makes this cold spot. Because this picture was done at 131 angstroms, not visible light. So when it gets cold, it doesn't radiate. And when it does, when it's hot, like in the flares areas, then you can see it's radiating a lot more. It's hotter. And it gets hotter than that in flares. You get X-ray emissions and things like that. All of this comes out and it hits the Earth's magnetic shield, which you see in the second photograph. This gets a little tricky because it hits in one place in the center and it kind of bounces, gets deflected off. And another place, it'll slide along the surface until it comes into these funnel-like things. And they end up channeling solar wind and solar radiation, the particle radiation, into the polar regions of the Earth, where the north and magnetic south poles are. And so you see on the charts, sometimes people will talk about, particularly if they're into global warming, they'll talk about how the polar regions are much hotter than the models say they should be. Well, they used to say that because they didn't include these effects in the models. So all of a sudden now they've got this big hot spot up on the North Pole. You know, it's degrees warmer than it should be, and it's not due to light, it's due to this particle radiation. They kind of act like funnels and catch this stuff. Of course, it's a very small amount of power compared to the total output power of the sun, but it's funneled and channeled and has an effect. And when you get into solar wind, it causes some certain things. You see Aurora Borealis and Australis. I didn't bring a picture of that, but there are hundreds of them online. It distorts radio propagation, and when it hits in when you get these solar events, it warms the outer atmosphere of the Earth, and it's been known to cause it to expand so that Starlink satellites get caught in it and get increased drag that causes them to fall back down to the Earth and re-enter. Mr. Musk did not like that. I think it was 28 of them. 28 of them to fall down. Of course, you know, there are like thousands of them. So one of the reasons he puts them so low is because that's the only place he could put them and not interfere with somebody else. Anyway, next thing on the list is the solar flare. Now, you probably hear people talk about these. This is a picture of one going off. And they cause streams of particles. Now, the standard model view of the solar flare, they talk about magnetic reconnection. But if you take the equations and you look at rapidly changing magnetic fields in the environment of a conductor, that makes an electric current. And so what you're really looking at is a lightning bolt on the sun, but huge, bigger than the Earth lightning bolt. And they can be, you know, tens of thousands of miles long and produce enough X radiation to ionize upper levels of the Earth's atmosphere, which is what's happening here. I'll get to this second one. That's actually something I intended to take out and got put in. When you get the solar flare, sometimes you get coronal mass ejections, which is this big pile of plasma that gets blown off the surface of the sun. The flare itself may be in the million megaton range. If it were a hydrogen bomb, it would be, you know, millions of megatons. So you get charts like this that show how it propagates out. Didn't happen to have one at the moment, but the top-down view, the polar view, you see here's the Earth and some of these others. Stereo A and Stereo B are satellites that monitor the sun. And they use Mars and Venus and all the rest. It's continually monitored now on the sun. This stuff is available from NASA sites. Now, one of the things you get about solar flares is how they affect technology. And we're going to have a side issue on plasma physics here. When these things hit the Earth's atmosphere. They induce ionization, plasmas. And there's a characteristic of plasmas called the plasma frequency. Below the plasma frequency, the plasma will look like any other kind of conductor. It will reflect electromagnetic radiation at that frequency and below. Above the plasma frequency, it's relatively transparent. So what this chart shows is a plot by color of the plasma frequency during a solar flare. And you can see this one happens to be hitting over the Indian Ocean, although I've seen them all over, all over. And this affects radio propagation, particularly at the AM bands and in that kind of area. Now you talk about UHF, it's above that frequency, so it doesn't get affected so much. But the AM frequencies, 1 megahertz and so on, will be affected by that, and it changes how they propagate. The second model of how the sun works, the not as popular model now, is based on an entirely different set of assumptions. The liquid metallic hydrogen model comes off of this phase diagram. Have pressure across the bottom, temperature across the top, and your normal temperature and pressure are along this line. That's normal. And pressure would be here for the Earth. The sun is, out here, and the dashed line is where the sun's temperature is. Well, that's the log of the temperature, so that's 1,000,000 times as much pressure and, thousands of times as the heat. 5,000 degrees, 5,800 degrees surface temperature of the sun, and this metallic liquid or boundary you get in the sun, and you also get it in Jupiter, is due to the incredible pressure. When the standard model of the sun was done that we talked about before, it was done in the middle of the 19th century. And they didn't know about this. They knew the ideal gas law, which is basically over here. And further research has indicated there are these regions out there that have to be accounted for. And there's a fairly extensive amount of debate on that subject right now. There are a lot of topics on the sun, and I haven't covered them all, but here are some that I missed, that I just happened to catch. Forbush decreases. This is a tricky one, because when there's a coronal mass ejection, the amount of cosmic rays, galactic cosmic rays, hitting the Earth decreases. And it's strictly due to the fact that there's all this stuff out there in the way. Then there's the Russell-McFerrin effect. Every year, twice a year, you get variations in the geomagnetic activity during the equinoxes. And that's, earlier this week was the equinox, and this effect is still happening. So you're getting a lot of solar wind kind of effects in the Earth at this time of year and in the spring. Then there's something called limb darkening. And limb darkening is it's a kind of a theoretical thing. If you look at how bright the sun is and you get a big round image, at the center it has a different brightness than out at the edges. And the limb out at the edge is not as bright as the standard model said it should be. So they call this limb darkening, and it's a matter of such a great deal of debate, and we're not going to talk any further about that. The last topic is solar granulation. Solar granulation is this material of the star's surface bubbling up to the surface in the top layer of the sun. It bubbles up. It looks kind of like a lava lamp a little bit, and it's all over the sun, and it makes these fluctuating bubbles. Granulation. So this is my presentation on the sun. We're talking about this. We've talked about the standard and the alternative model, how much sunlight we get, how much we get at the outside the Earth, at the Earth's distance. the magnetic fields, the wind, and all of that. The thing you have to remember in a talk like this, particularly given the larger subject, I don't know how to cover this very well, but this is all the result of God's design intent. And if you get bogged down on the details, you'll forget about that and get concerned only with the details. It's an occupational hazard dealing with this kind of stuff. So I encourage you to remember that this is the way He made things, not the way or at least it's what we think about the way He made them. It's not necessarily anything but there for a reason. So, kind of open for questions.
Could I ask you to do one thing?
Sure.
Without a question. Could you explain, you presented a chart of the solar flare cycles. Could you just briefly describe what that period is and where we are at this moment in time right now in that cycle?
Well, we're on the right edge of the page. And this is in years. So every 10 years you get a major division. What they do is they count the number of sunspots and plot it on this chart. Amy.
You mentioned also about I think you said a few hundred years where there wasn't any solar or sunspot activity.
Right.
What is that the only time that we have any historical evidence of that? Has there been other times? And is that something that could happen again,
Well, it could happen again, certainly if it happened before. Sunspots were discovered by Galileo when he first started using a telescope for astronomy. And so you're kind of limited to that kind of time scale. So like 400 years of counting this. We're now on solar cycle 25, which is this bump over here on the right. And this one was 24, 23, and so on. It's every 11 years. There are other cycles that are more than this. There's a 22-year cycle, because every other time the sun's magnetic field flips. So you get this 22-year cycle as well. And then there's one that's about 88 years, 80, 90 years that does this kind of dip and rise. And there may be others that we haven't studied long enough to figure out yet, but
So, go ahead. Follow on that. Are there predictions as to when the next period is going to be where there's not going to be these cycles? Going back to the 17th century.
well, they thought at the beginning of this cycle in 2020, they thought that this was going to be one of those. Because if you look, it's, fairly big, and then it gets smaller, and it gets smaller than that. They thought they were going to bottom out. But it didn't turn out that way. It bounced, and now we're going back to normal.
And that affects much of our...
That's a weather effect. During the years of the Maunder minimum, it got really cold in Northern Europe.
There's a little ice age or something like that.
Yeah, it's the mini ice age, they call it. And
So how does that affect technology?
well, technology would not be bothered so much by it. You wouldn't have solar flares messing up your radio. You wouldn't have a lot of other things. Astronauts, for example, really don't like some of these radiation effects coming out. And if you get up above the Earth's atmosphere, you're fully exposed to this. Everything, X-rays, particles, high energy particles, it's an incredible amount of stuff out there. Dan?
Could you make a comment on, I've heard, my whole life, the sun is just an average star. But then I've read things about the sun that are quite remarkable compared to other stars. Have you seen anything like for instance, its remarkable stability in its burning phase, where we're at right now?
Well, it varies some. Where did I do that chart? There. 1,361 watts per square meter. Typically, it varies about 1 watt per square meter either way, on the average. And so that's pretty darn stable. But the sun is in a group what's known as a main sequence star, and Alex is going to talk about that after I'm done, so I'm going to throw that one at him. But he's prepared for that kind of thing.
I was hoping. I'll wait.
And so, sir.
So, a lot of times we talk about the order of things, right? And I'm gonna be honest, I can't even fathom some of these numbers that you're talking about.
Yeah.
They sound massive.
Oh,
And-
there's a
and-
trick to that.
Right,
But
well,
go ahead.
So the question though is, you have, I'm looking at page 10 that shows this, the Earth's magnetic field that kind of acts as this, in my brain, how I would explain it, is this force field that can kind of help flip some of this off, right?
Yeah.
But what happens if the Earth was even a mile closer to the sun? Is there a calculation off of that?
Yeah, there is. A mile won't do it, but if you get too close, the temperature goes up, or the radiation goes up, or if you get too far out, the temperature goes down. But it's pretty much about where we are now.
We actually do vary by many miles over the course of the
Do
year.
we? Okay.
Yeah.
But in the grand scheme of however far the Earth is, right, or Earth from the sun, right, you're saying there's a variable, but if we were to get even just a touch too close or a touch too far, it would just, life would be done?
No, it would change the weather.
Okay.
You'd find that you probably didn't want to live in the equatorial zones if it got much closer. There's a problem with weather that we really haven't talked about. You know what a sling psychrometer is? It's the old way of measuring humidity. You take 2 thermometers, you put them on this thing you can sling around, and one of them has a sock on it that you make it wet, and you sling it around, and the wet one's colder than the hot one. If the wet one, called the wet bulb temperature, gets below 104 Fahrenheit, or pardon me, gets above 104 Fahrenheit, you're dead. Because your body won't be able to cool itself. And that has happened.
I think it's happening in Fort Worth.
Feels that way.
I lived in Houston. It was really high up there.
Well,
Towers we have in
I knew a guy once that lived in Recife, Brazil, and they didn't quite get that bad.
So, I have a question. I think I understand how the sun affects us because of the heat and the radiation. I mean, I sunburn, that's why I'm this color. But
Yeah, me too.
how does global warming here on Earth, how does it affect the sun or our weather? Does that make
Anything on Earth has a very minor effect on the sun. Jupiter has a slight effect on when the sunspots move and some things like that. But you could take the entirety of the Earth and throw it into the sun, and it wouldn't really notice much.
so global?
It's that big. I mean,
Okay. So global warming then is just what we're doing to ourselves just on Earth. It's not, nothing else out there is being affected by it? Or,
okay.
I'm sorry.
This is a can of worms.
Okay.
Okay. Global warming. You have the surface of the Earth and you have the atmosphere above it in various layers.
Okay.
The idea is the Earth gets hot and it radiates up, and the radiation gets trapped by the absorptive effects of the upper layers, and then gets radiated back down. Having said that, that's a real thing. Having said that, what you hear and mean by global warming in the general press, bunk. And the reason is that the major effect of this greenhouse effect is oxygen and nitrogen. And I didn't bring a picture of that part of the spectrum, but if you look at the transmission of the atmosphere, it does this way in the area called the mid-IR. And what that allows is the radiation that comes out tends to leave. And they test this. They measure it at, among other places, Hawaii, the University of Hawaii, with their big telescopes up on Mauna Kea. And you get this curve. That's in dry air. Now, they took a test cell and measured this, and they took the carbon dioxide up to 25 times normal. So it's 1% carbon dioxide, where normally you're 0.04. You get this little tiny bump here from 25 times normal carbon dioxide. You do 50% humidity water, you get 4 big things that completely go crazy, which everybody that lived in the northern latitudes will tell you that a clear night is apt to be colder than a cloudy night, and that's the same effect. So global warming is real. It's just not what they say it is in the models.
Okay, thank you.
So basically, we need to define what we mean by global warming, when we talk about global warming.
Yes. A rock, you take a rock and you put it around the sun, out in orbit, it has a surface temperature of about minus 20 Fahrenheit. Anything above that is global warming.
I mean, we've hit huge cycles of warming and ice ages when you zoom in at any of that. Other stuff was going on,
Right.
and that's pumping some stuff into the air.
Thank you for explaining.
I've got a great
Well, let's pick there. Lenny. Or
Andre?
Andre, pardon me.
Oh, I'm sorry.
You told us about AM radio transmission
Mhm.
affected by sun, but this is nowadays it's not that important, I guess. But people are worried about EMPs. EMP can destroy the whole, like all electronics and stuff.
Correct.
What do you tell about that?
Okay, back to this diagram. At the edge of the Earth's atmosphere is, the very outer part is called the ionosphere. And if you go up into the ionosphere and you set off an atomic bomb, which we have done in the past, it superheats things and accelerates the electrons in this plasma and makes more plasma. And when it hits the Earth's magnetic field, it bends. And when it bends like that, it makes a kind of radiation called Bremsstrahlung. The German word literally means breaking radiation, because it's going to break to the left and make the radiation. And it makes a lot of it, of course, being an atomic bomb, and that's what causes it. So it is kind of related, but it's a little off topic. Sir. I gotta be in the camera field. Sir.
Yeah, on page 3, you have the standard model of the sun with the core, radiation zone, etc. How does one derive that model? Is that purely theoretical, based on what evidence?
Whoa, there's a challenge. I've got a book at home that's about this thick called The Magnetohydrodynamic Model of the Sun that covers that. But basically, it's pressure collapse, and it gets hot, and of course you get the fusion reactions in the center. And they're going on fusion reaction rates, surface characteristics of the sun, something we haven't talked about called helioacoustics, where they watch waves across the surface of the sun. You notice how they can do that on the Earth, where they get models of the interior of the Earth because of earthquakes, and they listen to the earthquakes as they propagate. You can do that on the sun too, except you have to use a telescope. And it's a collection of a lot of different things. And there is quite a bit of controversy. As I said, the other model, with the liquid drop model, it doesn't compress as easy and so on. But I don't know how to answer your question any further than that. Am I getting the point across?
My understanding is that based on different experiments, whether it's gathering maybe satellite information, telescopic information, the best guess by physicists and astrophysicists, and is somewhat of an educated intellectual model.
Well, that's exactly what it is. It's a put together model based on probably hundreds of different pieces of data for a lot of different things. Sir?
When you talked about the cooling spot of the sun, I can't remember which page. Oh, page 10. I don't know why I'm obsessed with page 10. It's just, there are a lot of things that caught my attention there. You talked about this cooling space. Is this cooled to a temperature that, like, we could land? Or it's just cooled to a temperature?
No, it's the surface of the sun is about 5,800 Kelvin. That's
Good question.
what, about 6,000 Fahrenheit.
Tungsten melts at 4,000.
Yes, we're not going there. And but this is, it's cooled in the sense that the thermal emissions don't make as many of this 131 angstrom vacuum ultraviolet light. So it's cooler, but it's a relative term, not an absolute term.
Opportunity to go explore.
Right, none of that. Andy?
Staying on slide 10, solar wind.
Yep.
When I think of solar wind, when I think wind, I think atmosphere, the Earth's rotation. Since space is a vacuum, how does the solar wind blow towards the Earth?
That vacuum term is kind of tricky. Space is, we would consider space to be a hard vacuum, but it's not an absolute vacuum where nothing is there. The solar wind is a streaming gas, and it propagates out from the sun, and so it's blown out. Yeah,
So
it evaporates off the sun.
the force of the sun, the energy radiating off the sun just kind of pushes everything.
Yep.
in
Right.
one direction. Okay.
But the sun is heavy enough, it doesn't move. That's pretty.
Well, there's a lot more in the sun than just, the solar wind's a very small effect, but for the sun, the solar wind's a very small effect. For us, it's not. But,
We have a question right here.
sir?
Yeah, you mentioned earlier that the sun was really, really magnetic, or that there's a bunch of magnetic fields around it.
Yes.
Why is it that way? I mean, I know it has a lot of mass, so it's really gravitational, but what's with the magnetism? It's just a huge explosion.
Nobody really has a good answer for that. I can tell you, and Andy, Alex's shirt will confirm, that magnetic fields are caused by currents, electric currents.
Charged particles that are moving.
Yes.
A plasma is just charged particles that are moving. So
And it has to be a net charge that's moving, because if you move a positive and a negative together, it doesn't have a net effect. But that's in standard theory. Nobody really knows why it comes. They talk about, plasma currents and all of that, but it's, well, we can't measure them because they're down below the level of the photosphere and all of this kind of stuff. Well, it's a guess. That's what's causing it. It's a guess. And a lot of this is just that. It's a theory, which a theory means it's somebody's idea. And usually you want to have somebody's idea checked by some experimental result. Like we can look at the light coming from the sun and see the effects of the magnetic field. It's called Zeeman splitting. It causes the emission lines of hydrogen and helium and things to split into 3 lines because of the magnetic field. And you can measure how strong the field is by how much splitting you get. It's not an easy measurement at that temperature, but it can be done. So they can measure it, but saying why it's there, kind of tough.
All right, let's just take one more question. Bob, you have a question?
Yeah, I'd like to talk about the life of the sun. Each model you presented must have a predictable life of the sun. As the sun continues, gets older, it gets hotter. So, in our Earth, human habitation on Earth, where do we fit in there, a certain window, to where the temperatures on the Earth will allow us to live? What do they predict as to how long it will be until our temperatures on the earth will no longer be able to endure the heat from the sun.
The standard model, that's in the billions of years. I think the lifetime of the sun is something like 15 billion, something like that, if I remember correctly.
The temperature range on the earth will be able to, it's very sensitive here.
I don't think you'll have too much of a problem. I think, as I understand the way the model propagates, you'll correct me, Alex, I'm sure that you've got a billion years or so before the state of the sun changes into the next stage, which starts expanding toward a gas giant.
It's actually closer to 5 billion before
Is it?
that.
Okay. I don't think we need to worry.
Did you say billion or billion?
Billion with a B.
With a B.
Yeah, I think my talk will be done.
All right, let's move on to the next one, but thank you,
Okay.
Glenn. Thank you very much.